You've probably heard a ton about the promise of quantum computing, right? But what if there's a shortcut? A way to get that quantum-like power, but without all the quantum-level problems? Well, that's the whole idea behind a brand new kind of machine we're going to look at today, REZON. At the very heart of this new computer is a really simple but kind of profound question. What if we could actually teach waves how to compute? I'm not talking about ones and zeros, but the complex, messy, interfering dance of the waves themselves. This is the core idea we are going to unpack. So let's be super clear here. This is not a true quantum computer. It's something called quantum-inspired. And you can think of it as a brilliant workaround, a way to copy the raw power of quantum mechanics, but on hardware that we can actually build and run right now. And the dream? Well, it's absolutely massive, solving problems that are basically impossible for even the biggest supercomputers on Earth. But the reality? True quantum computers are incredibly fragile, they cost a fortune, and they need to be colder than deep space just to work for tiny fractions of a second. And this slide just lays it all out, right? On the left, you've got the monster engineering challenge of a real quantum computer. And on the right, you've got REZON. It runs at room temperature, it's stable for hours, not microseconds, and you can build it on hardware kind of like a standard GPU for just a tiny fraction of the cost. It's not even in the same league, practically speaking. Okay, but look, having a cool idea is one thing. To prove you've actually built a computer, you have to pass this one universal test. You have to master one of the most fundamental building blocks of all computation, the CNOT logic gate. So what exactly is a CNOT gate? Well, let's break it down. It's basically just a conditional switch. Imagine you have two light switches, a control and a target. If that control switch is off, the target switch does absolutely nothing. But if you flip the control switch on, it forces the target switch to flip its state. That simple if-then rule is the bedrock for almost every complex algorithm out there, which makes it the perfect stress test for any new computer. All right, so how did they actually try to build one of these things? Their first attempt was, well, it was beautiful in its simplicity. They just decided to let the raw physics of the system do all the work. This is where the story of turning chaos into order really begins. The whole idea was just so elegant. See, the REZON computer is built from these things called coupled oscillators. You can think of them like a web of tiny, interconnected wave machines. And the strategy was to just let the natural interference of all those waves perform the CNOT logic all by itself. Now, you've got to love how the researchers talked about this state. They called it a quantum soup. I mean, the system is just buzzing with potential, right? The waves are in superposition, exploring all these different possibilities at the same time. But it's too soft, it's too fuzzy and unstable to give you a clean, reliable yes or no answer. And yep, the results? They showed exactly that. About 70% of the time, it actually worked. But for a computer, a 30% error rate isn't just bad, it's completely useless. The raw physics was definitely onto something, but it wasn't a computer yet. It was pretty clear that this quantum soup needed a chef. And this, right here, is where things get really clever. This is the breakthrough. Instead of trying to fight the chaos and tame it, the researchers decided to just embrace it. They built a hybrid system. This was the big aha moment. What if all that messy, unstable quantum soup wasn't a problem that needed to be fixed, but a resource to be used? What if it already had the answer in it and you just needed a special kind of observer to read it clearly? And here's how they pulled it off. First, step one, you let the physical oscillators do what they do best. Go wild and explore every possible outcome in that chaotic soup. Then, and this is the genius part, a digital algorithm, this readout layer, acts as an observer. It doesn't interfere, it just watches the complex dance of the waves. And finally, in step 3, it interprets that super complex pattern and collapses it into a single, stable, definitive answer, a 0 or a 1. And the results of this hybrid approach? Take a look. It's perfect. This truth table shows every single case of the CNOT gate being handled with 100% accuracy. Every single time. The hybrid system totally worked. By combining the exploratory power of analog chaos with the precision of a digital observer, they built a stable, functional logic gate. Okay, so let's pause for a second and really dig into why this works. I mean, how does combining a chaotic physical system and a logical digital layer actually work? What's the secret sauce here? The answer comes down to this really cool concept known as the edge of chaos. It's that magical sweet spot that exists in any complex system. It's not rigid and perfectly ordered, but it's not complete random chaos either. It's this creative, dynamic state where a system is flexible enough to explore new things, but stable enough that it doesn't just fall apart. REZON is engineered to live right in that zone. So, you might be thinking, okay, in between sounds cool, but how in between are we talking here? Is that something you can actually measure? And it turns out, yes, you can. Researchers came up with this metric called the phase superposition measure. A score of 0 means the oscillator is a definite classical bit, a solid 0 or a solid 1. A score of 1 means it's in a maximum state of superposition, totally in between. And the average score for the oscillators in REZON? It's right around 0.5. That's the proof right there. The system consistently hangs out in that computationally rich, quantum-like state. This all leads to a really exciting conclusion. This success isn't just about one clever computer. This might actually be the dawn of an entirely new class of computing altogether. So, what's the big picture here? What does this actually mean? Well, this breakthrough points toward phase computers that can solve incredibly difficult problems, the kind that totally stump classical computers, and solve them in real time. And they can do it on common hardware at room temperature without the huge barriers of true quantum machines. This is a game changer for everything from logistics and finance to drug discovery. You know, this quote just wraps it all up so perfectly. It's not about choosing between the analog world of waves and the digital world of bits. It's about creating this perfect partnership. The physical system explores, and the digital system decides. A beautiful hybrid of chaos and logic. And this leaves us with a pretty fascinating final thought. For decades, we've been on a purely digital path. But breakthroughs like REZON suggest that by re-embracing the messy, chaotic, but incredibly powerful world of analog waves, we might unlock the next great leap in computation. Maybe the future isn't just digital. Maybe it's a hybrid.